Let's take a quick look at the finite square potential well and determine the transmission coefficient, T. The transmission coefficient is the probability that an incident wave, called psi sub I and C, makes it all the way across the well to the other side. It will be the ratio of the wave function's amplitude squared on the far side divided by the initial wave function's amplitude squared. Divided up into three regions. Region 1 is before the well. That's set up to be negative x territory, and it's at zero potential because the vertical here is energy, and outside the well the potential energy is zero. Only inside the well do you have potential energy of minus V0. The wave number then is just the standard square root of 2me over h bar. Rather, energy is h bar k quantity squared over 2m. In region 2, you have more oscillating solutions, but the wave number has changed because the energy separation between the wave and the bottom of the well has changed. We name the wave vector L, as Griffiths does, and call it the square root of 2me plus V0 to capture all that energy distance. Remember, V0 is a positive number. In region 3, we're back to the same potential level as original, so it's essentially the same function. But notice in region 1, I wrote the wave function as a e to the ikx plus b e to the minus ikx to indicate the possibility that you have both incident wave and some reflection. When the incident wave arrives at the first potential change, there will be reflection. There always is. And then when the wave again arrives at the next potential change, there will be another reflection, which is why less probability amplitude emerges at the output of the well than went into it. In region 3, there's no need for an e to the minus ikx term. That is, there's no need to assume that there's backwards propagating wave. It's only going forward because we're saying the incidence is in region 1. So we're going to apply continuity and differentiability at these two places, x equals 0 and x equals 2a, and we're going to do it with the expressions from each region separately. And our ultimate goal is to find the ratio of f squared divided by a squared, because a e to the ikx depicts the incoming wave and f e to the ikx depicts the outgoing wave. The modulus amplitude squared is the probability amplitude of the wave being in region 3 divided by the probability amplitude of the wave being in region 1. And of course there's a 100% chance that the wave is incoming. F squared over a squared is the probability that the wave exits. Continuity at x equals 0 is written as the wave function minus, meaning whatever the wave function expression is just before x equals 0, evaluated with x equals 0, equals the expression for the wave function just beyond x equals 0, evaluated with x equals 0. So in other words, the region 1 wave function at x equals 0 equals the region 2 wave function at x equals 0. On quick inspection, I think you can see that that means a plus b equals c plus d. Call that equation 1. The differentiability condition evaluated at x equals 0 is also something you can probably just envision in your mind. You take those derivatives of the region 1 and region 2 wave functions and then evaluate them at x equals 0. You have this expression. We'll call it equation 2. At x equals 2a, it's a little messier. The continuity condition is written as the region 2 wave function evaluated at 2a, the region 3 wave function evaluated at 2a. We'll call that equation 3. Finally, the differentiability at the boundary at x equals 2a is this, and we'll call that equation 4. Now we begin some algebraic manipulation, and there are a lot of ways of doing this, and sometimes you'll see this done with matrix methods, but since it's only 4 equations and 4 unknowns, and our goal is to just get the ratio of 2, f over a, I'm just going to do substitutions until I get it. The quickest way to eliminate b is to take equation 1, multiply it through by k, then add it to equation 2. And when you do that, you get that, and we'll call that equation 5. We'll get rid of d with a very similar trick. Multiply equation 3 by L and add it to equation 4. And you can check that's equation 3 times L, and this is equation 4, and when you add them together, you've gotten rid of d. Call that equation 6. Finally, let's eliminate c by taking the difference instead of the sum. Do you see that if I turn this plus sign right here into a minus sign, I will get this expression, which we call equation 7. Take expressions 6 and 7 Sub them into equation 5. Equation 5 was this thing, 2ka equals k plus lc plus k minus ld. Sub them in. You still have 2ka, you still have k plus l, but c needs to be taken out of equation 6. So take equation 6, put c on one side and everything else on the other side, and put it in for c. And so that's the result over here. This is c with an extra factor of k plus l. And then the same for d. Take equation 7, put d on the left side and everything else on the right side, and sub it in right there. And there's d with an extra factor of k minus l. That's the result of combining these three equations, 5, 6, and 7. Our goal is to get the transmission coefficient, so let's get a divided by f on one side. That's simply a matter of bringing the f over to the denominator and bringing the 2k over to the other side. There's a over f, and the transmission coefficient is the mod squared of that. It's 1 over the mod squared of that. So let's get the modulus squared of this expression. 1 over t is the mod squared of a divided by the modulus squared of f. There you go, it says it there. Take the modulus squared of the numerator. I replaced e to the minus 2ILA with cosine and sine. And same here, 2ILA with cosine and sine. Oh, and by the way, I also moved the e to the 2IKA from the numerator into the denominator, and it became e to the minus 2IKA. Forgot to mention that. And the reason for doing that is so that when I take the modulus squared of the denominator, that just simply vanishes, and I never have to see it again. And so the modulus squared of the denominator is just 4kl squared, 16k squared l squared. The next step is to group the imaginary and real parts and take that modulus squared. We use this rule. The modulus squared of a complex number, a plus ib, is simply the real part, a squared, plus the imaginary part, b squared. We're going to do that to the numerator. So you have the real part, and I squared it, and you have the imaginary part, and I squared it. At the same time, I had to group the real and imaginary parts together. K plus L squared times cosine 2LA minus K minus L squared times cosine 2LA is the real part, and that's what's squared here. K plus L squared times sine of 2LA, negative, minus K plus L times sine 2LA is the imaginary part, so that's what you see here. And now you've got a real part and an imaginary part, and use this rule. A plus IB mod squared is a squared plus b squared. So that's the real part squared. That's the imaginary part squared. You can divide out the 16k squared l squared for the first term. Can't quite take it all out for the second term. That's helpful. We want this to look like equation 172 in Griffiths. That equation looks like this. It's 1 plus stuff. Well, there's no 1 plus up here, so we need to make that happen. Well, you know cosine squared plus sine squared is 1, so add sine squared 2LA to all of this. When you do that, you can make an adjustment with this sine in front of the 2k squared L squared to make that happen. And this is how I'm doing it. I'm going to add 2k squared L squared, and then I'm going to take away 2k squared L squared. So you could just think of it as add 2k squared L squared, and then take away 2k squared L squared. So then I can move 4k squared L squared over here, over 4k squared L squared, and I'm left with this. So just follow the algebra, make sure you can see that. And another thing is that k to the fourth plus l to the fourth minus 2k squared L squared is k squared minus L squared quantity squared. Make that adjustment there. Now we can sub in values for L and k. So we had these definitions of L and k, just put them in there. Root 2m over h bars cancel. You see how there's 4 of them upstairs and 4 of them downstairs, and they're gone. They cancel. And so you're just left with that. 1 over the transmission coefficient is 1 plus e minus k squared gives you an e, minus L squared gives you a minus e minus v0. And you have k squared, which gives you an e, and L squared, which gives you an e plus v0. Put in what L is. You have e minus e, so get rid of that. And you're done. And that's how we get to equation 172 in Griffiths. That's what I meant to make very clear to everybody today. I just was too rushed. As was this, but you have play pause you can push now.